Log on, tune in, find out. Another good idea from Cambridge.
He's carried on to work on a variety of problems more recently. He and colleagues have discovered some rather interesting results, which he's going to report on today and I think tomorrow also. So I'd like you to welcome Dan.
Oh, thank you very much. I'm one of those people in that picture with more gray hair, but less less hair to be gray. All right, let me find the talk here. Okay. Lovely. All right, so I'm going to be talking about, I should say, some recent progress on multi-state perfect phylogeny. This is an area that we've been working very intensively in for the last couple of years. Fume Lam, who's not quite here yet, will also talk a little bit about some additional work when she gives a 20-minute talk. So, as you all remember, when I finished my talk in 2007, exactly where I was. So I'll just start immediately from that point on and with no introduction. No. But this talk is actually a continuation of what I talked about in 2007. So some of the slides, 3 or 4 of them, are identical, in particular this one. So this is the perfect phylogeny problem for binary sequences. Let's start out by defining that. Let's see, there's supposed to be a laser, yeah. So in the binary case, what we have is some ancestral sequence, in this case 5 sites. I'll just note the states of each character as a 0 initially. And what happens over time is each character mutates from state 0 to state 1. So what's happening in this tree that's depicted here are the sites or the characters that mutate. Character 1 mutates here, and what you can see is that the sequences below that point all have a 1 at position 1. Here's where character 3 mutates, and below there, you have a 1 at position 3 there, but nowhere else. Now, the key point about the perfect phylogeny model is you only have 1 mutation per site allowed. So site 1 or character 1, I'll use those 2 words interchangeably. Character 1 mutates only here in the whole history of these sequences, and character 4 mutates there only once in the whole sequence, in the whole history. And that's justified by the infinite sites assumption in population genetics. It's obviously not true in all phylogenetic situations, but for sufficient actual biological applications, it is true. Now, mathematically, when can we derive a perfect phylogeny for binary data? That's been known and discovered and rediscovered many times in many different contexts. And here is the basic theorem. In population genetics, it's called the 4 gametes condition. In phylogenetics, it's more often called compatibility. There's splits equivalence. And I think if you search, you could probably find 10 or so different independent derivations of this. But it's for binary data. There's a perfect phylogeny if and only if there's no pair of sites that contains all 4 gametes. It is all 4 binary combinations 0, 0, 0, 1, 1, 0, and 1, 1, 0, and 1, 0. No, there's a little error there. And 0, 1. I've used that slide for 10 years now, and I never noticed that. Oh, well. All right, but now so the world of binary is more or less understood. There's still some results in binary, but that's more or less settled. We're interested in going beyond binary, and this little slide, which I'm going to pass through, gives you some biological hand-waving why we might be interested in that. Mostly, the big open embarrassing question in this whole multi-state perfect phylogeny question is, what are the real biological applications? But this is a mathematically oriented group, so we'll just assume that it must have some. So in the 3-state perfect phylogeny model, what we have is data. This is the taxa, and these are the characters, A, B, C. And the state of taxon 1 of character A is 3, and for taxon 2 it's 2, and so on. So these numbers generalize the 0 and 1, which was in the binary case. They don't have any intrinsic meaning. These values just partition the set of taxa. So this is the ones 3, 1 and 3 are in the same class, and 4 and 1 are the same class here, and so on. So what's required now is a tree where the leaves are labeled by the individual rows, by the individual taxa. So here's a 2, 3, 2. That's taxon 2, 2, 3, 2. And the tree has and then we also label the interiors with some vector derived from here. It doesn't have to be identical to one of the leaves, but in this example it is. But the key point in a multi-state perfect phylogeny, let me give you an example. The key point is that whenever you focus on a particular character, let's say character B, and you focus on a particular state of that character, that's, for example, state 2, and then you find all of the vertices where character B has state 2. So it's this vertex, this vertex, this vertex, this vertex, and that vertex. When you find that particular subtree, when you find those particular vertices that are labeled with state 2 at character B, that subtree, that set of nodes should be a subtree. Okay, that's the requirement. If I just give you an arbitrary tree with node labels, and you find the nodes that are labeled where character B is labeled with 2, it wouldn't necessarily form a subtree. It could be disconnected. The convexity requirement is that it is a subtree. Okay, and I'll give you another view of what convexity means that makes it more sensible in terms of the binary case, makes it look more like the binary case. So if we have a perfect phylogeny that satisfies the convexity requirement that I just told you about, I should also emphasize, for every character and for every state of the character, when you look at the nodes in the tree that are labeled by that state of that character, that particular tree, that particular subgraph must be a tree. Okay? That particular forest must be a tree. All right. Now, here's another view of what that means. If you just take the tree, which I say satisfies that requirement, and now you arbitrarily choose a root, and you direct all the edges of the tree away from that root, and then what happens is that any character can mutate into a given state at most once. That happens at most once, but never mutates into its root state. That's a consequence in an alternative definition. And then this view makes the k-state perfect phylogeny a natural generalization of the binary case. In the binary case, we permitted every character to mutate from 0 to 1 at most once. Now we're saying for every character and every state of the character, you can mutate into that state at most once. There's this little degeneracy about the root states, but otherwise, that's a more intuitive definition. And so here's the same tree that I had before, the same perfect phylogeny, and now we see this view in action. I just rooted it arbitrarily here, and here's where we're seeing B mutate from state 2 to state 3. And that mutation of state 2 to 3 into 3 only happens once. Here's a mutation of B into state 1, and that only happens once. Okay, everybody clear what the multi-state perfect phylogeny is? Because that's obviously, if you're not getting that definition, then the rest of the talk is completely wasted. So let me know. Okay. All right. So the basic multi-state perfect phylogeny problem is given data where we have k states per column or per character. Does there exist a multi-state perfect phylogeny? And I'll tell you something about the history of that problem later on, but basically the problem as stated is NP-complete, but with important restrictions has polynomial time algorithms. The first thing I want to talk about, and unfortunately Fume isn't here yet, is a generalization of the four gametes condition. The four gametes condition, which we saw a minute ago, which was the case of explained when a binary perfect phylogeny was possible, really has two parts to it. The first part says there's a perfect phylogeny if and only if there's a perfect phylogeny for every pair of sites. Okay, because the four gamete condition, as I stated earlier, was there's a binary perfect phylogeny if and only if for any pair of columns or for any pair of characters, none of them has all four of the gametes. So it's a pairwise type condition. In the second part of it, a single pair of sites has a perfect phylogeny if and only if it does not have all four gametes. So if we divide up the four gamete condition into these two parts, then in generalizations, we might be able to generalize the first part, but not the second, or the second, but not the first, or we can generalize both of them. Okay, so generalization could be one or the other. Now, a generalization for the first part for three states was studied in 1975. I should mention this problem, the literature on this problem mostly appears in the 70s and 80s, and then there are some additional papers through the 90s, but fairly sparse until recently. There's been a real resurgence of interest. Fitch in the 1975 showed examples with three states where there's a three-state perfect phylogeny for every pair of sites, but there's no perfect phylogeny for all of the entire data. So this was an attempt to get a pairwise generalization to three states of the four gametes condition. It's just a natural thing one would try. And Fitch showed, Walter Fitch, which a name I hope many of you know, sort of the original computational phylogeneticist, showed that wasn't going to be possible. And Meacham generalized that in 1981 that showed for every R, there's an example where every subset of R minus one characters has an R state perfect phylogeny, but the whole data does not. Okay, so this was the natural generalization to R states, R minus one characters. Each subset of R minus one has a perfect phylogeny, R state perfect phylogeny, but the entire data lacks one. They drew a conclusion from that, which is in fact was too strong, which is good because it meant that nobody worked on that for 30 years until we look back at it. This is what they said, or this is what Meacham said. The Fitch example shows that any algorithm to determine whether a set of characters is compatible, it has a perfect phylogeny, must consider the set as a whole and cannot take the shortcut of only checking pairs of characters. Okay? Well, the second phrase, and cannot take the shortcut of only checking pairs, is correct. Okay? And in fact, it generalizes to subsets of R minus one. But the first phrase really is incorrect, or at least it doesn't follow from what they showed. The Fitch example shows that any algorithm to determine whether a set of characters is compatible or has a perfect phylogeny must consider the set as a whole. It doesn't have one of these nice subset type possibilities. But we, and it's a shame Fume is not here yet because we is a shortcut for Fume. No, I did something on that, but overwhelmingly, Fume's result here is that there's a three-state perfect phylogeny for given data, if and only if there's a three-state perfect phylogeny for each triple of sites. So this is really a natural generalization of the binary perfect phylogeny, the binary case, generalizing the first part. And the proof uses Bunneman's theorem, which I'm going to talk a lot about in the second part of the talk, and a very exacting case analysis. So this paper was in Recom 2009, and it's in press now in Siam Journal in Discrete Math. Okay, what about the second part of the four gametes theorem? What is it in the second part of the four gametes condition? It said that if you looked at two characters at a time, when did that have a perfect phylogeny? And that was when you did not have all four gametes. Okay, what is the situation in the case of three states and is three characters? So how How is that generalized to 3 sites or 3 characters in 3-state data? And we were able to figure that out as well. And it turns out that the answer is that there are 4 forbidden subpatterns. So in the 4-gamete condition, there's only 1. There's 1 subpattern. If you avoid that subpattern, then you have a perfect phylogeny. In the case of 3 states, there are 4 forbidden patterns. That is, 3 sites will have a 3-state perfect phylogeny if and only if none of these 4 forbidden patterns appear in the 3 sites. So here they are. Here are 3 characters, A, B, C, A, B, C, and here there are 4 different patterns. And I boxed this part just to show that these are identical. These parts are identical. Then the parts below here differ. There's some kind of similarities you can see. Those are identical, and so on. And then the 4th one looks different. And this is actually Fitch's example. So once we derived what the 4 different forbidden subpatterns were through a lot of circuitous mathematics, and then there it was, then we quickly looked back at Fitch's example to make sure that one of the 4 that we derived was equal to Fitch. Otherwise, we were in big trouble. And thankfully, one of them is exactly Fitch's example. And so here they are. And what do they mean? I mean, in the 4 case, maybe because I've lived with this so long, the 4-gamete condition somehow seems sensible and has some intuitive meaning, although maybe it's just purely mathematical. But these, they don't mean anything to me. And so it's just, and of course, all this is up to relabeling and permutations and so on. But, here's Fume, it's just arrived. Okay, so what do these mean? I don't know. I'm just going to give an advertisement for what Fume is going to talk about in detail. I don't know when, tomorrow or the next day. Can we go beyond 3 states? So what I just told you was the paper that is in Siam Journal on Computing. Beyond 3 states, here's what Fume, and I wasn't part of this, except for looking over her shoulder, has derived. For any R greater than 3, if you have a problem instance with the most R states, there's an R state perfect phylogeny for the problem instance if there's an R state perfect phylogeny for each subset of R plus 1 characters. Okay? So in the case of 3, when R is equal to 3, we had the result that 3 states at a time was sufficient. Now the result is that if, let's say, you go up to 4 states, then you have to look at 5 characters at a time. 4 states, this theorem does not say that 4 states at a time is sufficient. So we have a gap. Meekum's constructions show that you need R minus 1 characters at a time. That's necessary. And Fume's result says we need that R plus 1 are sufficient. And R lies in between. So we've got this little annoying gap. So how are we going to close that gap? You can either come up or down, or you can stay ignorant. Now there actually was some progress sent to us just about a couple of weeks ago. And this is going to be a paper in WABI 2011, which I think is in August or September. For 4 states, there is an example where every 4 characters has a 4-state perfect phylogeny, but the full data does not. Okay? So maybe the fact that the sufficient condition was R plus 1, maybe there's a reason for that. Okay? But it's a strange place to have a change. Often there's a change in problems between 2 and 3. But this is a case where there would be a change from 3 to 4. Where for 3 states, 3 characters are enough, but for 4 states and maybe beyond, you need 1 more. Okay, so now what I'm going to tell you about different part of the talk is general K-state perfect phylogeny problems, how we solve them, and variations on them. And this actually will give you some technical introduction to the kind of approach that Fume will be talking about when she gives her talk. Okay, so when we talk about various different problems, the existence problem, given M, that's the matrix of characters in taxa data, and K, that's the, K is equal to R. we're K-state. A minute ago was R-state. All right. We're mathematicians, or you're mathematicians, and you can deal with that. So is there a K-state perfect phylogeny for the data? All right, that's the existence problem. Missing data problem is the same as before, but now some of the cells don't have values. So can values less than or equal to K be imputed so that the resulting matrix M prime has a K-state perfect phylogeny? Okay, so can you put them in there? If you don't restrict the states to be less than or equal to K, then actually this has a fairly simple solution, which I learned about by reading Mike's book, Mike and Charles' book, and gave me a moment of panic. Say, wait a minute, it says a simple solution. Oh, okay, the number of states isn't being restricted. Okay, but with this, the problem is NP hard. Handling missing data extends the utility of perfect phylogeny model, obviously. In fact, for biological applications, I think you all know that missing data is very real. And there's a third variant, which I'm going to talk about, which is removable data. But let me talk about existence and missing data first. So what's the existence problem, the status of existence? There's a polytime algorithm for 3 straight states, that's Dress and Steele, 93. A polytime algorithm for 3 or 4 states, Kanan and Warno, 1994. It's the same Warno who's sitting at the back. A polytime algorithm for a fixed number of states, polynomial in N and M, but you have to fix the number of states, K. That was due to Agarwala and Fernandez-Baca, and then a speed up of that method by Kanan and Warno in 97. And when K is not fixed, the existence problem is NP hard. So existence has some very beautiful algorithms. But when there's missing data, those particular known algorithms don't generalize to handle it. At least I haven't been able to see how to generalize those algorithms. In the end, you're left with just enumerating brute force enumeration of values, and then you can test each one to see if it has a perfect phylogeny or not. So we need another approach for the missing data problem. Well, what actually has been done on the missing data problem before we, well, it's NP complete for K equals 2. However, there's effective practical approaches for K equals 2. This is one of my papers in 2007 in the conference Cocoon. And in fact, I talked about that, well, in a moment. And then the Satya Mukherjee has a nice paper on handling this in practice in TCBB. And there's a polynomial method for a directed variant when K equals 2. A very elegant, beautiful algorithm by Shamir and others. And then for K equals 3, 4, and 5, I actually talked about that right here in 2007 using integer programming. And that's been published since that time. Okay, but for the general case, when K is not limited to 3, 4, and 5, what do we do? So this one I'm going to talk about today, and this was published in Journal of Computational Biology in 2010. So everything is based on both existence and missing data, and the third variant that I'll talk about later is based on an old theorem, a beautiful old theorem, and many newer techniques. So the old theorem is called Bunemann's theorem, which I used to call Bunneman's theorem, but Tandy corrected me recently, Peter Buneman, that relates perfect phylogeny problem to chordal graphs, and this is about 35 years old. And then many newer techniques and theorems on minimal triangulations. It's a very, very rich literature in graph theory on minimal triangulations, and some of it we were able to steal to make the results on perfect phylogeny problem. So the minimal triangulations of a non-chordal graph to make it chordal, and the literature on minimal triangulations is current and ongoing. It's huge. It could be 100 papers or more, and just full of wonderful technique. So the basic thing that we did was take Bunemann's old theorem, which was conceptually very, very nice, but not useful computationally, and then apply a lot of the some newer things from the minimal triangulations literature to become an actual computational technique, and then played around with many different variants. So I want to talk about that approach. And technically, this is some of the same material, or the background that you will need for Fumi's talk. So what is a chordal graph, by the way? A graph is chordal if every cycle of length 4 or more contains a chord. Chordal graphs are also called triangulated graphs. So here's one. Here's a cycle, okay, of length 4 or more, and it has a chord. It has an edge across it. Here's another cycle longer than 4, and it has an edge across it. And you can see why it's called triangulated, because you take a cycle that doesn't have a large cycle, it has to have a chord. Well, that just makes a smaller cycle, it has to have a chord, and so on, and ultimately becomes triangulated. It's not necessarily planar, but it is ultimately, every cycle, you end up with these triangles. Now, this definition is actually the original definition, but it doesn't suggest why chordal graphs are so useful. We'll get, no, actually, we won't get to a definition that tells you, which suggests why they're so useful, but they come up all over the place in many, many different applications, huge numbers of applications, almost always showing what can happen when things are nice. It's the perfect, elegant, happy case. All right, so here's Bunemann's theorem. First of all, here's an example. Character 1, character 2, character 3. And if you notice, I've colored them. I guess character 1 is black, character 2 is red, and character 3 is some kind of bluish thing. And Bunemann builds a graph called the partition intersection graph. And what it has is one node for each, well, it has one column of nodes for each character. And it has one node for each state in that character. So character 1 has 3 different states, so we have 3 different nodes here. Actually, I haven't put the nodes there, but I put the labels on the invisible nodes. There's a node there, a node there. And C2 and C3 also have 3 states. And then, for each row, for each taxon, you create a clique which connects the states of the characters. So this is 3, 2, 1. In character 1, that's 3, goes to character 2, which is 2, goes to character 1 in C3, and then back. So that's a clique, okay? And I've only put the clique on there for row 1. You would also put one for row 2, et cetera. And obviously, the graph gets very, very messy, which is why I didn't put them all on there. But that's how you build the partition intersection graph. It's the union of cliques, one clique per row. All right, and each row is fairly well defined. And obviously, if the matrix has little m characters, then that partition intersection graph is an m-partite graph, and the nodes associated with a single character are given distinct colors. All right, just the way we talk about things. And then an edge, which is not in that graph, is called legal if the 2 endpoints of the edge do not have the same color. So legal edges can go between nodes of different columns in that partition intersection graph. Nodes that go between edges that go between 2 nodes of the same color are illegal, and those are called a monochromatic pair. Okay, so just going back to this picture, so the partition intersection graph is this superposition of these cliques, and any edge that's not there is either legal or illegal. It's legal if it's an edge that goes between 2 nodes that are not of the same color, maybe they're not in the same column, and illegal if it goes between 2 nodes of the same color. So this distinction between legal and illegal is going to be critical. All right, any questions on that? Again, that's critical. So here's Bunemann's theorem. There's a perfect phylogeny for M if and only if legal edges can be added to the graph to make it chordal. Okay? So you have this partition intersection graph, which you can build very quickly. That's certainly efficient. And if it's chordal, fine, you're done. And in fact, for binary case, a necessary and sufficient condition for a binary perfect phylogeny is that it is chordal at that point. But for k bigger than 2, it may happen that the graph is not chordal. And yet, you can add legal edges to make it chordal. Or maybe you can't add legal edges to make it chordal. But Bunemann's theorem says that if you can add legal edges to make it chordal, then there's a perfect phylogeny for the data. Okay? And the graph, once you've added the additional legal edges, if it's chordal, is called a legal triangulation of the partition intersection graph. So that's Bunemann's theorem. It's beautiful. The proof is also very elegant and ties into some deep ideas in chordal graph theory, particularly clique trees and so on. But when Bunemann initially proved it, he didn't see, or we didn't see, the world didn't see the connections, the full connections. So it's just sort of a proof on its own, and it looks like just weird stuff. Now it makes a lot more sense. But how do we use that as a computational tool? knowing what legal edges to add, or if there is legal edges to add, that doesn't seem like a simple problem. And as I mentioned earlier, the problem of, without restricting the number of states, the problem of knowing whether there's a perfect phylogeny or not is NP complete. So this problem of whether or not we can pick legal edges to add certainly seems difficult. But I'm going to solve it in linear time. No, I'm going to solve it in some methods that actually work. I won't violate P and NP. But one thing that one can do in legal time is this. If you have a legal triangulation of the partition intersection graph, then you can use that to derive a perfect phylogeny for the data in linear time. So Bunneman's theorem says there is a perfect phylogeny, but it doesn't say how you actually get your hands on it. Well, it does implicitly. But I'm just pointing out here that this can be done in linear time. So, and I'm not going to talk about that, just to say, so the real problem is there a legal triangulation? Because from that point, getting the perfect phylogeny is very simple. All right, so here's an actual example. Oops, now, okay. The characters used to be letters and the taxa used to be numbers. Now it's the other way around. Okay, but again, in this audience, that shouldn't be a problem. And so what I have is one node for each character state pair as required in the partition intersection graph. And so this is character 3 state 0. Yeah, character state pair, character 3 state 0. And as it turns out, if you don't put the nodes of individual color in columns, but they are colored here, you can lay this graph out so it looks plainer, and that's a nicer view of things. So this is the partition intersection graph of this data, just not put in columns. And as it turns out, there's a one-to-one correspondence between the maximal cliques in here and the taxa. Okay, and that's the superposition of the cliques that made the partition intersection graph. All right, so this is the clique that comes from row B. You see it has state 0 at character 1, state 0 character 1, etc. I'm too tired to be able to go through an example. I slept on the floor in San Francisco airport when I wasn't waiting in line for 12 hours to get here, but I'm glad I'm here. So, okay, a legal triangulation. Here is an example of a legal triangulation. In that graph that we were looking at here, this is not chordal. It's not chordal because here we have this big cycle and there's no chord between it. But here we can add a chord between a gray node and a red node and make it now chordal. It's legal, it's a triangulation, and we now have another two triangles here, two maximal cliques called X and Y. And the linear time algorithm that I said I wasn't going to talk about can transform that triangulation into a perfect phylogeny for the data. So here's a perfect phylogeny for the data, and what you have is one node in the perfect phylogeny for each maximal clique in the triangulated graph. This is again very beautiful, rich theory about chordal graphs and triangulations and so on. Okay, so what do we do about missing data? Now, so Bunneman's theorem was not about missing data per se. If M is missing data, we can still build the partition intersection graph using the known data in M. We just, instead of building full cliques, we build partial cliques. Bunneman's theorem still holds. That is, there's a perfect phylogeny for some imputation of missing data in the matrix, if and only if there's a legal triangulation of the partition intersection graph. The legal triangulation gives a perfect phylogeny, and then once you get the perfect phylogeny, you can impute the data. And I think this theorem with missing data was not the way Bunneman stated it, but I think it's implicitly in Mike and Charles's book. So that's not something I'm claiming is new, but it's a critical ingredient into what we're doing. So the point is that conceptually now, this is if we have missing data here, this element is missing, we don't know what it is. When we built B, instead of being a clique that involved a node from character 1, character 2, character 3, we built a clique that involved a node from character 1 and character 3. In other words, just a single edge. It went from character 1 state 0 and character 3 state 0. So here's that edge that corresponds to this row. And in general, it could be a clique. It's a clique. Well, it is a clique. It's a clique on the number of states, the number of characters that have known values for that row. And Bunemann's theorem still holds. If you can add edges, legal edges, to make this chordal, then there's a multi-state perfect phylogeny. If you can't, then there isn't. Oh, and you can. There it is. Well, of course, we knew that. Okay, so the key problem is, well, to say, this partition intersection graph is now conceptually perfect for modeling missing data. Okay, but is it solvable? I mean, it expresses the missing data problem very nicely, but what do you do about it? So the key problem is still, how do you find legal triangulations? How do you add those legal edges to make it triangulated? Do we know how to do that? That's, NP hard problems I mentioned earlier, and there are some triangulations problems that are very well studied that are NP hard also, tree width, minimizing the number of added edges, and so on. But there is a robust and still expanding literature on efficient algorithms for finding minimal triangulations of a non-chordal graph. I'll tell you what minimal is in a minute, but the main point is that we can get away just by focusing on minimal, and there's a huge literature of efficiently adding edges to make a minimal triangulation. So a triangulation of a non-chordal graph is minimal if no subset of added edges is a triangulation. So obvious use of the word minimal here. And it's clearly true that if we can find a legal triangulation of a partition intersection graph, which means that there's a perfect phylogeny, we can find a legal triangulation which is minimal as a triangulation, okay? So that means that we can steal as much as possible from the literature on minimal triangulations. And I'll show you in a minute, there's a very, very powerful theorem about minimal triangulations. They don't have the added criteria, the added requirement of legality, but so that's our contribution of seeing what to do about legality. But let me tell you about minimal triangulation. The key object in that whole literature is minimal vertex separators. Okay, so we've got minimal here in two different senses. I think we'll end up with 6 or 7 of them. No, there's a lot of minimal and maximals coming up. So a set of nodes whose removal separates vertices u and v is called a UV separator. And S is a minimal UV separator if no subset of S is a UV separator. That's okay. So S is a minimal separator, and S is a minimal separator if it's a minimal UV separator for some vertex pair UV. Okay, now the reason that we're being so particular here is that I can show you a minimal separator which has contained in it another minimal separator. Okay, so that at first sounds very confusing because that seems to violate the notion of minimality. And the point is that you have to pay attention to its minimal for some UV. So we can have a separator which is a minimal separator for UV, and it contains within it another separator which is minimal for some different pair. Okay, but nonetheless, if we call a separator minimal, it's because it's minimal for some pair. All right. Now, the next thing of importance is the notion of crossing. A minimal separator S crosses a minimal separator S prime if S separates some pair of nodes in S prime. So separators are subsets of nodes, and separators separate nodes. So if you have one separator S, it certainly could separate a pair of nodes that are part of a minimal separator S prime. If that happens, then the two separators are said to cross, and that's a symmetric relation for minimal separators. Okay? So S crosses S prime crosses S. Here's an example. Here's our graph again. If I take away 2, 1 or 3, 2, that's a minimal separator. It separates these nodes from these nodes, and it's minimal. I could pick a pair of nodes that it separates, and no proper subset of these two would still be a separator, a separator for these two. And similarly, symmetrically, this is a separator for any pair of nodes in here and here. And these two separators cross, okay? Because if I take this separator, I've separated this node from this node, okay? So those are two crossing minimal separators. When the graph is planar, crossing has a nice pictorial meaning, but for non-planar graphs, you just have to look at the set definition. And here's non-crossing, and again, because it's planar, it looks non-crossing, okay? So we have notion of minimal separators and crossing or non-crossing minimal separators. Now, a complete characterization of minimal triangulations of a non-chordal graph was derived in 1997. So a couple of years ago, I don't know, 3 or 4 years ago, I got the idea I should really start reading this triangulation literature, and I started back in, before 1997, starting reading the literature, and you can see people kind of creeping up to this, getting more and more general, until finally, the general theorem was found, and everything previous to that was irrelevant. Completing a minimal separator means adding all the missing edges between pairs of nodes in S to make S a clique. Okay, so you have a minimal separator. If I add all the edges in there to make it a clique, that's called completing it. And here's the capstone theorem. Every minimal triangulation of a graph is obtained by completing each minimal separator in a maximal set of pairwise non-crossing minimal separators. Okay, let me read the converse part. Conversely, completing every minimal separator in a maximal set of pairwise non-crossing minimal separators yields a minimal triangulation. So you find, so here's a recipe for finding a triangulation, a minimal triangulation of a non-chordal graph. You find the minimal separators, which I'll tell you how to do in a minute. You find a maximal set, maximal in the set sense, of minimal separators that are pairwise non-crossing. Pairwise non-crossing we sometimes call parallel. So a maximal set of pairwise non-crossing minimal separators. And then each one of those minimal separators, you complete them, which means you add all the edges to make them a clique. That will be a minimal triangulation. And every minimal triangulation can be derived in that way. That's what the Perrin-Scheffler theorem says. And so it tells us a recipe for finding minimal triangulations. But we want minimal triangulations, but we want them to be legal. Okay? Still, this is very powerful because it is sufficient for us to find a minimal triangulation that happens to be legal. So we can use the Perrin-Scheffler theorem. So by the way, here's an example of Perrin-Scheffler. There are 6 minimal separators in this. 1, 2, 3, 4, 5, 6. Okay? There are 2 maximal sets of 5 pairwise non-crossing minimal separators, which you can try to find. And here's a triangulation which is illegal, okay, but obeys the Perrin-Scheffler theorem. So this is a minimal triangulation, but it's illegal because it added an edge between 2 nodes of the same color. And here's a legal minimal triangulation. It obeys the Perrin-Scheffler theorem, and the edge that is added is legal. Okay, so how do we use this? One more definition. A minimal separator in the partition intersection graph is called legal if it does not use an edge between 2 nodes of the same color, and it's called illegal if it does. Okay. A minimal separator. Well, this is sort of screwed up. A minimal separator is a set of nodes. Okay. So what does it mean about using an edge? That's if you complete it. So, but the proper definition when you're just looking at a set of nodes is that you have 2 nodes of the same color. Okay. So a separator is legal if it does not have 2 nodes of the same color, which does mean that when you complete it, when you add in all the edges to make it a clique, you will not add in you'll not add an edge between 2 nodes of the same color. Okay. Then it's called legal. Otherwise, it's called illegal. Is that clear? I got to fix this slide someday. Okay. Oh, you're nodding, so I assume it's right. It's okay. All right. So we have legal and illegal minimal separators, and we can use the Perrin-Scheffler theorem to prove the main result, which is the following. There is a perfect phylogeny for M, even if M has missing data, if and only if there is some set Q of pairwise non-crossing, now legal, minimal separators that separate every monochromatic pair of nodes in GM. So remember what monochromatic was, they have the same color. So now the problem is you've got your partition intersection graph, and you find all the legal minimal separators, which may mean you have to find all the minimal separators and then sort them out into which are legal and illegal, but sometimes we don't have to do that. So you find all the legal minimal separators. Then you want to find a maximal, well, this doesn't say maximal, a set Q of pairwise non-crossing legal minimal separators that separate every monochromatic pair of nodes in the partition intersection graph. And I'm not going to go into the proof of this. This is the main result of the paper I mentioned from JCB in 2010. Okay, but that is our main theorem and our main tool now for solving. Yeah, this obeys theorem 1. Okay, hint of the proof now. Corollaries of that theorem are actually very powerful because empirically, I'll show you get to the empirical part in a minute, the corollaries solve the problem without having to do any fancy footwork. So if there's a monochromatic pair of nodes that is not separated by any legal minimal separator, then obviously there's no perfect phylogeny. You can't pick a subset of legal minimal separators that in the end separate every monochromatic pair if there's some monochromatic pair that isn't even separated. If the partition intersection graph has no illegal minimal separators, then M has a perfect phylogeny. Corollary 3, if every monochromatic pair of nodes is separated by some legal minimal separator and no legal minimal separators cross, then M has a perfect phylogeny. So we have these three simplifications of the main theorem. So again, here's the recipe for solving perfect phylogeny with missing data is find all the legal minimal separators. For each legal minimal separator, determine which monochromatic pairs of nodes it separates and which legal minimal separators it crosses. Then determine if any of the corollaries hold, because if the corollaries hold, it tells you you're done. Some of those corollaries said there's no perfect phylogeny, some said there was. If so, there's no perfect phylogeny in corollary 1, or a set Q needed in theorem 1 can be found greedily. So okay. If no corollary holds, then what you have to do is set up and solve a straightforward integer linear program to find a set Q of pairwise non-crossing legal minimal separators that separates every monochromatic pair of nodes in GM. It's basically just a node cover problem at that point because you found what pairs of legal minimal separators cross. You have to forbid taking any two that cross. You found which monochromatic pairs of nodes are separated by a legal minimal separator. You have to throw into the integer program that each one of those pairs is separated by one, and that's it. Okay? And then you let the integer program find it. If there is a feasible solution, then you can greedily extend Q to be maximal, set of pairwise non-crossing legal, etc., to find a legal minimal triangulation, and from that you find the actual tree. Okay, this is all mathematics, but does it actually help in practice? Again, we're focused on a NP-complete problem, so maybe all of this was just, well, mathematics. Yes, it works. Now, probably for this audience, I would have told you about this anyway, even if it didn't work, because this is, there's enough theory interest here. But for people with practical interest, it actually works. We've done simulations, vast numbers of simulations. We use the program MS to generate the data, which is a very popular program in population genetics. It generates data of the size of interest in population genetics and a lot of phylogenetics, but not on the genomic scale, not genome-sized data or tree of life type data. I'll show you in a moment. And here's what we found empirically. The minimal separators are found very quickly. So the bottleneck of this whole method is finding all the legal minimal separators, or finding all the minimal separators. I didn't say that it was something we could do efficiently. However, there's an algorithm, off-the-shelf algorithm. It takes cubic time per minimal separator. But we do have methods which we didn't even need to use to speed this up, and that's another paper which did come out last year on methods that speed things up. Theoretically, when there's no missing data, all the legal minimal separators can be found in nm squared worst case time for any fixed k. So in polynomial time, you can find all the legal minimal separators when there's no missing data. So it's only when there's missing data that the problem of finding all the legal minimal separators is even a problem. Of course, even when we find all the legal minimal separators fast, if we have to run an integer program, then we're back to a problem that's NP hard, integer programming. But I'll talk about that empirically in a minute. So it turned out that finding the minimal separators is not a bottleneck. It just simply wasn't a problem at all, empirically. The observed number of minimal separators is actually small. In theory, it can be exponential, but it isn't happening in the data that we generate. And there are very few crossing pairs of legal minimal separators, so that's not a problem either. And until a very large percentage of missing data, until there's a huge number of missing data, most problems are solved by the corollaries. You don't even need to set up the integer program at all. So that's all, it's all very fast. And when an integer program is needed, it's tiny. For the existence problem, we can actually prove that the size of the ILP is polynomially bounded. So empirically, the ILPs solve quickly. In our empirical cases, when we've had to go to solving an ILP, we use Cplex. Cplex reports out to some number of digits how long the ILP took. We've never seen one that took more than 0.00 seconds. Okay? So Cplex just solves that integer program instantly from its perspective. Now, I guess if we asked for more, there's no magic here. It did take some time, but so little that it's not reportable in these 3 digits. Okay. In fact, most of the problems solve in the Cplex preprocessor. So if you know what Cplex is, it's an integer programming package, and before it goes into the hard part of an integer programming solver, it tries to reduce the linear inequalities, and if it can reduce them down to nothing, then it has a single solution. That's what's in the preprocessor. So most of the problems that actually ran solve in the preprocessor. And here's a slide that nobody can read that shows you all kinds of numbers that justify what I was saying. So although the chordal graph approach may seem impractical, it actually works on data of sizes that are of current interest. So I'm going to go back here and just try to read it here. We're looking at problems up to size 100 by 100. So 100 taxa, 100 characters, and then up to 80 by 80, we looked at 20%, up to 20% missing data. Okay, so that encompasses certain kinds of applications. In molecular data and population genetics, that's way bigger than is in reality. In phylogenetics, it probably is not. I mean, you can certainly find examples where there's more missing data. So let me tell you a little bit about when there's no missing data. I think I've already said that you can find all the legal minimal separators in polynomial time, and so that speeds up. Now, another structure, more structure, Fume proved the following thing. When k is equal to 3, back to the 3 states, the main theorem that I quoted, which required finding a maximal set of pairwise non-crossing minimal separators. So the pairwise non-crossing added a complication. She proved that for k equals 3, a necessary and sufficient condition for the existence of a 3-state perfect phylogeny is every monochromatic pair of nodes is separated by some legal minimal separator. So the non-crossing part is gone. So obviously much, much simpler, and this does not extend to k equals 4. Another example where in perfect phylogeny, the break between things that are really, really nice and not as nice is between 3 and 4, not between 2 and 3. And using that, this implied fairly quickly an algorithm to decide if a 3-state perfect phylogeny, 3-state problem has a perfect phylogeny in time that was equal to existing algorithms that I mentioned earlier. But surprisingly, we couldn't initially see how to use all the machinery to actually find how to construct one. We have now solved that, and that's going to be a Wabi 2011 paper by Geisel, Lamb, and myself. So again, sort of a strange thing that with all this heavy machinery, for k equals 3, we can see fairly quickly whether it has a perfect phylogeny or not, but actually constructing one took another year to figure out. Okay, let me just very quickly talk about removable data. this is the character removal problem. Given data that does not have a k-state perfect phylogeny, what's the minimum number of characters to remove so that the remaining data does have a k-state perfect phylogeny? This is a very standard thing that's done in phylogenetics. If your data does not fit a nice model, you just knock out some of the columns until it does. And you want to minimize the number of columns that you knock out. So this is generalized to k-states. Here's a much more, there's a different variant of it. When there's missing data and there's no solution to the missing data problem, what's the minimum number of characters to remove so that the remaining data does have a solution to the missing data problem? Okay? Rob Geisel, a student of myself, have an ISBRA paper in 2010 that uses the same machinery, the same chordal graph machinery, to set up an integer program for this problem, for the knocking out columns problem. You can again formulate an integer linear programming using the chordal graph view. And we can speed up the finding all the minimal separators. But the only thing I want to say about this is that now we have to focus on illegal minimal separators as well as legal minimal separators. And here's the main theorem, that these problems are solved by finding a minimal triangulation which may be illegal. So before we were always focused on legal minimal triangulations. Now we want to find a minimal triangulation that might even be illegal, but maximize the number of legal characters it contains. Okay? So when you have a triangulation, 3 minutes? Okay, thank you. And again, we can cast this as an integer programming problem. And here are the empirical results. Good enough or I wouldn't be talking about it. Okay, you probably don't want to see more than that. So the character removal problem can be cast in this way. There's software available. Other results, 3-state perfect phylogeny existence problem can be reduced to 2-sat. This is just basically stealing a paper of Dress and Steele where they solved that problem from scratch. And in reading that paper, we realized that one could look at it as reducing the problem to 2-sat. And for those of you who are in computer science, you know that 2-sat is one of our holy something or others. We love to look at things as 2-sat. Another paper, so that's by myself and Yufeng Wu, who should also be at this meeting, but I don't see him. And then another student of mine showed how to reduce the k-state problems to 2-state problems, to binary problems, but binary problems with missing data. That can be reduced in polynomial time, and then you can hit it with all kinds of machinery for 2-state missing data, and that works. And the final result that I'll mention, the missing data removal data problems were examined under the rich data hypothesis, which I won't tell you about, and generalizations of it. And polynomial time algorithms were given. This is by Stevens, and Bonnie McCormick, I think is her name. I didn't remember her name when I wrote these slides, and I didn't finish that. Bonnie McCormick, or Bonnie Kirkpatrick, sorry. All right, well, I think I should stop there. I don't know if I have time for questions, or? Thank you.
There's time for a few questions. Yeah.
Over here. Yeah. When you used the ILP in the middle of the talk, and you said it performed magically, did you look at the linear relaxation of it? Does it have some special properties?
Well, yeah, the question is whether the integer program, if you took a look at the linear relaxation, does it have any properties? I don't know, but I think the fact that the preprocessor is solving it, the preprocessor is not taking into account any of the integrality constraints. The fact that the preprocessor is solving most of these suggests that at least probabilistically there are some properties there that could give you a theorem.
So you gave the pattern that's needed for 2 states, not linear, and for 3 states. Is there a similar set of forbidden patterns for 4 states?
Okay, so we know the forbidden patterns for 2 states and for 3 states. The 4-state question was just mentioned, answered not by us, but that you need to look at 5 at a time. And you're asking about forbidden patterns. I do have a student who's trying to find all the forbidden patterns for 4 states. He has many, but he doesn't have a proof that he's found them all. So that's essentially open.
How many do you think there are?
How many did he? I don't know. I think he's up to 10 or 15. It's going to be a lot. Yeah.
Well, I'm not sure if I really understood the question, but my understanding from what you've told me is that each character can, or each state can only appear once. It can't have independent sort of
Yes.
manifestations in different parts of the phylogeny. Now that clearly doesn't sound all that practical. Now I'm just wondering whether you could make it into a more practical sort of phylogenetic problem if you were to think about a different kind of missing data, where you would say, let's say state 3 would appear in 2 different branches. One you might call 3A and one you might call 3B, but that A-B status would be kind of a missingness. This is a different kind of missing data problem, but I just wonder whether you could take your methods to approach that problem.
Yeah, okay, so that problem generally is called parsimony, which you probably know, the parsimony type question, where you allow the same mutation to occur more than once in history. And I'm not aware of parsimony problems being solved with all this machinery. Obviously, there's a very big literature on parsimony problems and ways in which people approach it. But I'm not aware of chordal graph approach in looking at parsimony questions. Actually, Fume might know more about that. So yeah, I don't know. As for whether or not these problems actually occur, the one mutation, allowing one mutation in history, that's an assumption that's very central in certain parts of population genetics, and mostly for very recent mutations. So it does have some reality. And in terms of phylogenetics, we just justify it by saying it's a complex trait. So there's certainly, I mean, we all know that there's convergent evolution and all sorts of things. But for most complex traits, that seems like an acceptable assumption.
One more, 2 more questions. Go ahead.
And I could briefly mention what the picture looks like when you take recombination into account.
Okay, well, when we have recombination, that's another area that I've worked on. Yes, I don't know how to use this machinery at all for recombination. And that does remind me of one thing. Oh, not on the slide. A shameless advertisement. I and the 2 other co-authors are writing a book on phylogenetic networks with recombination. And I didn't want to carry a stack of papers here, but I'll print out a draft of that book and have it somewhere on display so people can look at it and give me comments.
So if I understood correctly, so if the data meets all the constraints, there's a perfect phylogeny. But there could be an alternative phylogeny which might be more likely from a maximum likely point of view? Oh
yeah. There are multiple solutions in general, and we have not added any kind of. We could add some constraints, some costs into our model. Whether they would be able to model likelihood, I don't know. So we certainly have not done anything in terms of a likelihood or Bayesian approach or any kind of probabilistic approach at all. This is all with an objective function. Yeah.
Okay, so we'll break for coffee, but let's first thank Dan for a fascinating talk.